For those students that would like it, I will review the 3.4 section assessment and take a look at the problems that involve some mathematics. And these are all dealing with density. Number 52, a weather balloon is inflated to a volume of 2.2 times 10 to the third liters. Okay, so, whoops, that was my cat that just jumped up on the desk. 2.2 times 10 to the third liters is my volume. Okay, and it says that I also have 37.4 grams of helium. And I need to find the density of helium in grams per liter. So density equals mass divided by volume. So this is a simple division problem. So we have 37.4 grams divided by 2.2 times 10 to the third liters. And our density would be 1.7 times 10 to the minus second grams per liter. Notice that the density of a gas is expressed in grams per liter, not grams per milliliter. And the reason is that we need a larger volume to express our mass in, because the particles of gas are spread so far apart. If we were to measure the mass of that gas within just a milliliter, there wouldn't be much there. So we'd have a very, very tiny little mass. So the densities of gases are expressed in grams per liter, whereas solids and liquids are expressed in grams per milliliter. In number 53, we have a 68-gram bar of gold. And it's cut into 3 equal pieces. So basically we're dividing this into 3 pieces. And the question is saying, how does the density of each piece compare to the density of the original gold bar? What you need to remember is that density is intensive. That means that this property does not depend on the sample size. It only depends on the composition of the sample. So those 3 pieces of gold that were cut from the original gold bar have the same composition, so they will still have the same density. It will not vary at all. Number 54. A plastic ball with a volume of 19.7 centimeters cubed. There's our volume. Has a mass of 15.8 grams. So 15.8 grams equals our mass. Would this ball sink or float in a container of gasoline? Well, we need to know the density of gasoline. And there's a table on page 90 of your book that lists the density of common substances. And the density of gasoline is about 0.66 to 0.68 grams per milliliter. Okay, so let's find the volume of this substance. Okay, or I'm sorry, the density of this substance. So the density would be 15.8 grams over 19.7 centimeters cubed. Okay, when we calculate that density, we would get 0.802 grams per centimeter cubed. And when we compare it with the density of gasoline, 0.66 to 0.68, and remember that grams per milliliter is the same as grams per centimeter cubed, we find that this density is larger than the density of gasoline, so the ball would sink. In number 55, what's the volume in cubic centimeters of a sample of cough syrup that has a mass of 50 grams? So we know the mass is 50 grams. The density is 0.950 grams per centimeter cubed. So we need to find volume. Okay, so let's think what we're starting with. We're going to start with our given, and I'm going to change colors here so it's easier to read. There's my blue. Okay, I'm going to start with 50 grams. Okay, I can use my density as a conversion factor. my density is expressed in grams per centimeter cubed. And guess what? I want to find volume in centimeters cubed. So if I put centimeters cubed in the numerator of my conversion factor, that's the units I'm going to end up with. And when I'm reading density, what this means is that in 1 centimeter cubed, there is 0.950 grams of mass. So I've set my problem up. When I look at my units, grams here is in the denominator, grams here is in the numerator. So grams and grams cancel out, and I'll be left with centimeters. So when I do my math, I'm taking 50 divided by 0.950, and this ends up being 52.6 centimeters cubed of volume. Okay? So I've simply taken my given density and used it as a conversion factor. Now again, if we remember that density is mass divided by volume, if I want to solve for volume, and I'm going to do it algebraically here by multiplying both sides by volume, so I get it to cancel out here. I have volume times density equals mass, and then I want to get volume by itself by dividing both sides by density. Okay, so that cancels out. I end up with volume equals mass divided by density. I could have just plugged those numbers in. I could have taken 50 grams divided by 0.950 grams per centimeter cubed. But guess what? 50 grams divided by 0.950 grams per centimeter cubed is the same thing as 50 grams times 1 over 0.950 grams. It's the same thing operationally, so we've done the same thing. So using the density as a conversion factor will give us the same result as solving for volume in the density equation. Number 56. What's the mass in kilograms of 14 liters of gasoline? So we have 14 liters of gas. Let me put a little line here to separate that problem out. Assume that the density of gasoline is 0.680 grams per centimeter cubed. So the density is 0.680 grams per centimeter cubed. Okay, so I want to find the mass in kilograms. I'm looking for mass in kilograms. I have my volume in liters. This is my volume here. But my density is in grams per centimeter cubed. Well, if I can get my density in kilograms per liter, then I can do this problem. So, if I have 0.680 grams per centimeter cubed, and I want to change this to kilograms per liter, first I'm going to convert grams to kilograms. I'm going to use a conversion factor. I want kilograms on the top. That's what I want. Okay, so in 1 kilogram, there's 1,000 grams. Okay, so grams and grams would cancel out. Okay, I also want to get liters. All right, so I want my centimeters cubed to turn into liters. So I want this value here to be liters. So I'm going to put liters down on the bottom. In 1 liter, there is 1,000 centimeters cubed. So I've set up my problem with 2 conversion factors. But guess what? When we look at these 2 conversion factors are inverses of each other. And they themselves cancel each other out. So 0.680 grams per centimeters cubed equals 0.680 kilograms per liter. So now I can do my problem. All right, I have my volume. That's 14 liters of gas, 14.00 liters. All right, I'll draw a line here to separate this from my actual problem. Again, I can use my density as a conversion factor. I want to find the mass, okay? I want to find the mass. I know that the density is 0.680 kilograms per liter. So I want to convert this. So I know that I've got 0.680 kilograms per liter. When I look at my conversion factor, liters and liters cancel out. I'm left with kilograms. That's the unit I want because I'm solving for mass. So I take 14 times 0.680 and I get 9.52 kilograms of gasoline. Okay? So again, we're using the density equals mass divided by volume equation here. I could have simply solved for mass, and mass is density times volume, and I could have just plugged those variables in. All right, I would have ended up with the same answer. Instead, I used density as a conversion factor to get my liters to cancel out and be left with the units of kilograms, which is my unit of mass. But operationally, it is the same thing because here I've taken volume and I've multiplied it by density. Volume times density does equal mass.